Hello everyone, my name is Jordan Hernandez and today I'll be going over Demo 3 Learning Target 7B. So what is Learning Target 7B about? Learning Target 7B is defined I can convert and or not circuits into circuits composed of only not and nor gates or nor gates. So what are not gates and nor gates? Not gates are going to be a regular AND gate, however, it's going to be a opposite or it's going to negate right afterwards. And the same thing for an OR gate, it's going to be the opposite of an OR gate, but it would have a negate right afterwards. And what both and not and nor are is that they are both universal gates, so we can convert them actually into different expressions. So before we go into that, we can see that this is what a NOR gate would look like, and we can see what a not AND gate is going to look like as well. Now, for our universal gate formulas, this is how we're able to convert it into regular expressions. So we can see from not AND, whenever we need to convert it into a AND gate form, it can basically have the not gate right after the not AND gate. But if we were to convert it into an OR expression, we can have the NOT gates before our OR. And the same thing for our NOR, we'll have it right afterwards. We'll still make it into a regular OR expression while we have the NOT gates before. With the NOR gate afterwards, we'll basically make it into an AND expression. So for our example today, we will start from a unsimplified equation. Our equation is going to be Q is equal to AB prime plus prime over AC prime times A prime plus B prime. And what our normal circuit of this equation is going to look like is going to be looking like this. As you can see, we can have our AND gate right here is going to represent AB prime. Our AND NOT gate is going to represent this whole equation with the NOT gate inside being C prime. And then this expression is going to be represented in this OR gate expression. Then when we combine the two with the AND gate, it's going to be representing this last part. And then finally, when we have this last OR gate, it's going to represent the whole equation adding at the end. As we can see, 0, 0, 0. All values are 0. It would output as 1 in this expression. Now, for our not AND version of this circuit, as we can see previously, when we have both our OR gates right here, it will convert it as a NOT gate before the not AND. And for anything that's regularly with an irregular AND gate, we will see we had to convert it to a NOT gate before the NOT, or sorry, the NOT AND gates before the NOT gate. And when they're all 0, it still equals to 1. So we can know that this actually is basically the same circuit. However, our next step is going to be involving to get rid of any double knot versions or any double knots. And usually any double knots are going to be, as explained, any knots of a circuit line that has two knots in the same line. So as we can see right here, we have this knot and this knot. We'll be getting rid of this knot and this knot. We'll also be getting rid of, and then these two over here we'll also be getting rid of. So if we were to simplify this, it would look like this. And then finally, we will go to our final form, which is going to be called our dual symbols circuit. And usually for our dual symbol circuits, we'll have a negate OR gate to represent each of our addition problems in the equations. And if we look back here, we had an addition problem when we had both the values of B and A inside of it, and when we have it last for our equation. So when we convert it all to our dual symbols version, it would look like this. And this is the negate gates as well. It's a more cleaner look to them rather than having the NOT gates right before these equations. And then as we can see right here too, forgot to mention that when they're all 0 again, it still outputs as 1. So we could know that all these guys are all the same equation and are all the same at once. This is the end of Demo 3 Learning Target 7b. I hope you all enjoy, and I'll see you all next time.